Okay, so imagine that we're trying to send a message into outer space, and we're really limited with how much space that we have to send our message in. So we want to be really smart about how we encode each letter to a certain number of bits in order to maximize, in order to minimize the amount of space that we take up. Because if we don't have a lot of space and we're trying to send data in a not smart way, we're not gonna be able to send our whole message. So how do we do this? The idea is that in English, right, we know how frequent on average each letter takes up. So for example, we know that E comes up a lot and Z not really. So it wouldn't really make a whole lot of sense to have E be the same number of bits as Z if they don't, if E occurs a lot more. So the idea is we want to somehow use this idea of knowing the frequencies to assign them a number of bits to minimize, on average, how many bits we're sending across per word. Okay, now let's just assume that we already know how to do this for our language, just to make this more fun. Okay, so now let's assume we're sending messages out, but we get a message back from an alien. Okay, that's enough. Okay. And they're sending messages back in a different language. Okay, now let's just say we're trying to be slick and we just start responding. Like, we know that their letters here are only going to be B, L, A, R, G. Okay, and we start responding using our same, right before we had said that we can, knowing the English frequency, right, in our language, how to send bits across. But if they're using a different language, they're gonna have a different frequency. And so it's not gonna make sense for us to use our own mappings now if we're dealing with a language that has letters come up in a different frequency. So the idea is, let's say we got in a tremendous amount of their data, of their received messages, and we were able to get the frequencies for each letter, right? We want to build a new bit mapping so that we can minimize the number of bits in our messages that are being sent back across. So that's what we're trying to do. Okay, so I'm gonna erase all this. Okay. So our goal minimize number of bits per letter. Okay, that's what we want to do. Okay, and then so now I wrote this down just to like make it clear. But the way we do this is with something called something called Huffman coding. And we recently learned about this in one of my math classes that I'm taking. I thought it was interesting, so that's why I wanted to make this video. Kind of cool. But okay, so let's start writing out the frequencies for each of these. So I remember our letters were B, L, A, R, G. So let's just say we have B as 0.23, L as 0.04, A as okay. So the steps for this is we want to start building trees. And we want to build trees based off of so these are the weights. You can use these as the weights for each element. We want to combine the two smallest weights into one tree, and we're gonna put our heavier elements on the left. Okay. So we see that our smallest weights are L and A, so we're gonna combine them. So our heavy elements on the left, right? So A is gonna be on the left, L is gonna be on the right, and our new weight for this tree is gonna be the sum of these weights, so 0.10. Now we move everything down. So B is 0.23, R is 0.11, and then G is 0.56. Okay, so now we look, what's our two smallest elements? It's gonna be these ones. Okay, so now we're gonna come down here. R is gonna be over here, AL, and then our new weight is gonna be 0.21. Okay, keep going down. Can't write in space, yikes. Okay. Okay, now we're gonna combine these ones. Right, so 0.23 and 0.21, those are two smallest. What do I wanna go for this? Yeah, I'll just keep going down. So, okay, A, L, R, B. Yeah, and so this is gonna have a total weight of 0.44. And now, so we're just left with G. So okay, and you know you've done this right. If your total is 1, I messed it up before and it was not 1. But yeah, okay. So now you want to combine these ones, and it's the last step. So you have it's gonna look like this. Okay. Our new total is gonna be 1. So we're done. Okay. And now, what do we do with this? So now we can just arbitrarily pick either left or right to be 1 or 0. It doesn't really matter. Let's just pick left as 1. Left as in the left branch or the right branch. Okay. So now we just read from our root down to there, and that's the number of bits, or that is the bit encoding. So we have G. We're gonna represent G with the bit 1. B is gonna be 0, 1. R is going to be, this is confusing, I'm gonna get rid of this because this isn't a weight. R is gonna be 0, 0, 1. A is gonna be 0, 0, 0, 1. And then L is going to be 4 zeros. Okay. Now, how do we find, now we're pretty much done. How do we find the average bit cost per letter? So what we want to do now, I might bring this into the middle actually, just so it's easier. Yeah, probably starting right bigger. Okay, so the average bit cost per letter. What we want to do is multiply not the bit values, but the number of bits in each letter by its frequency. Okay, so we have 1 for G, so it's going to be 1 times the frequency, so 0.56. Now B is 2, because it's 2 bits. It's 0 and 1. If it was 0, 0, it would be 2. If it was 1, 1, it would be 2. It's just the number of bits. So 2 times 0.23. R is going to be 3 times 0.11. A is going to be 4 times 0.06. And then L is going to be 4 times 0.04. Okay? So now we're going to sum all of these up. So, yeah, I guess we're going to add these. Okay. So this is going to be 0.56. So 0.56 plus 0.46 plus 0.33 plus 0.24 plus 0.16. Okay, we add all these up. So this one is like this, and then I think this should be right. So this is a 1. And if I've done this correctly, what Huffman coding guarantees is that this number, what we've just found, you cannot get smaller than this. With these frequencies, if you were to have written these out in any other way, you could not get an average less than this. So kind of cool. And now we can start sending messages back to the aliens, which is even cooler.